Okay, today we start with the definition. Suppose let G be a group. So let G be a group, and if we take an element, so let A is an element of G, then we are collecting the elements which are commute with A. We call that is N of A. Sometimes they call CL of A, but anyway both are the same. So N of A is nothing but we are collecting the elements P in G such that AB equal to B. So we are collecting elements B which is commutes with this particular A. That is A we call is a normalizer. So this set is called normalizer of A. Okay, or is sometimes called use the notation C of A, centralizer of A. Okay, they use any notation. So N of A is nothing but collection of all elements which are commutes with that particular element E. Okay. Now we define the new set Z of G. So this is nothing but collection of all elements G in G is satisfy the commutative property with every element of G. So when we collect the G, this G satisfies the commutative property, that is GH equal to HG for all H in G. So that is Z of G. We call the center of G, center of the group G. And the Z of G is always normal subgroup. This Z of G, we can easily show that is a normal subgroup. This is very important subgroup. In any group, we have a normal subgroup that is center of G. So center of G is a collection of all elements which commutes with every element of G. So clearly identity element is a member of Z of G because identity element satisfies the commutative property with every element, that is EG equal to GE for any G. Therefore, identity element satisfies the commutative property to all the elements of G. Therefore, identity element is a member of the subgroup Z of G. And then suppose we take two elements A, B in Z of G, we can easily show that the AB inverse is also in Z of G. And we can show that it's a normal subgroup. Okay, so this is very important subgroup. Subgroup is called center of the group. Okay, so finding the center of group is a problem. Okay. Now, what is the relation between this N of A and Z of G? Okay, so there are some notes. If suppose the group itself is a abelian group, then Z of G equal to G. Okay, so that is the first point. So that is, if G is abelian group, if G is abelian, if and only if the G should be equal to the center of the group G. So G equal to Z of G if and only if G is abelian. It's a very, very important point. We can easily prove it. Okay, because we are collecting Z of G, we are collecting elements which commute property with every element. Since G is abelian group, therefore all the elements satisfy the commutative property with the other elements. Therefore G is abelian if and only if G should be equal to Z of G. Now, what is the relation between this Z of G and then N of A? So N of A is nothing but we are collecting elements which are satisfy the commutative property with the particular A. But Z of G is nothing but is satisfy the commutative property with every element. So satisfy the commutative property with every element, therefore in particular satisfy the commutative property with A. Therefore the second property, the subgroup Z of G is a subgroup of N of A. So this is clear. So how to prove this one, this containment? So you can take arbitrary element in Z of G. So let H in Z of G. Now what we have to prove? We have to prove H is a element of N of A. That is what we have to show. This A and H are satisfy the commutative property. So since H is an element of Z of G, implies that H satisfies the commutative property with every element. Therefore, this is equal to H into G equal to G into H for all G in G by the definition of Z of G. So this H satisfies the commutative property with every element of G. In particular, it satisfies the commutative property with the element A. So in particular, HA equal to GH, sorry, AH. HA equal to AH. Since this H satisfies the commutative property with this A, implies that H is a member of N of A. Therefore, that H is a member of N of A. So Z of G is always a subset of N of A, where A is any A. Okay. Now, suppose we are taking the intersection of all N of A, then what will happen? That is the next property. Suppose I am taking N of A and take the intersection varies over all the elements of G. So this is nothing but Z of G equal to Z of G. If we take the intersection of all N of A, should be equal to Z of A. But if you take single N of A, Z of A contains, sorry, N of A contains Z of G. So the proof of this is trivial. Okay, again, so we have to prove the two containment. Okay, so how to prove this one? So already we know that Z of G is a subset of N of A for any A. Since Z of G is contained in all N of A, therefore Z of G contains the intersection of N of A, is contained in intersection of N of A in G. Now we have to prove the converse containment. Suppose we start with the element in intersection of N of A. So let suppose we take some Z is in intersection of N of A, where A in G. So that means what? That Z belongs to N of A for all A. So implies that since Z in the intersection, therefore Z belongs to N of A for all A in G. This is small Z, okay? So otherwise you can take some other letter. Suppose I take X. So since X is a member of N of A, implies that X satisfies the commutative property with A, but this is for all A. Since this X satisfies the commutative property with every element of group G, therefore this X should be in the Z of G. Because it satisfies the commutative property with every element. Therefore we start with the element here, and that element should be in the Z of G. Therefore, the intersection N of A is contained in Z of G, where A runs over all the elements of G. Therefore, combining 1 and 2, maybe we call this is 1 and this is 2. Now from 1 and 2 we get a equation. So from 1 and 2 we get this Z of G. Center of G is intersection of all N of A, where A varies over the group G. It's very important. These two subgroups are very important. So one is the normalizer or centralizer of A, another one is the center of the group G. So the relation between N of A and Z of G is Z of G is always a subset of N of A, but we can write Z of G as the intersection of all N of A. Okay. So it's very important. Okay. Now we have another thing. So in a group, when we say two elements are conjugate, suppose we have two elements, let A, B in G. So we say A is related to B, or sometimes called A is equivalent to B. So when we say A is equivalent to B, if and only if there is an element, another element C in G, such that one element can be written as C times B C inverse. Then we say A and B are equivalents. Now this relation form an equivalence relation. Okay, so equivalence relation means what? this should be reflexive. So reflexive means what? A is related to A for any A. So that is reflexive. Now next one is symmetric. So symmetric means what? A is related to B implies B is related to A. This is symmetric. And third one is the delta is transitive. Transitivity. So that means what? Suppose A related to B and B related to some other C implies that A related to C. So this relation satisfies these three properties: reflexive, symmetric, and transitive. So if this relation delta satisfies these three property, then we say this relation is an equivalence relation. Equivalence relation. So when we say a relation is equivalence relation, we satisfy the three property: reflexive, symmetric, transitivity, and three property. So once we have an equivalence relation, we have equivalent class. So equivalent class of A, suppose we take one element, we take arbitrary element. So let A belongs to the group G. Suppose G have a equivalence relation delta. Now we define the new set CL of A, that is conjugate class. Okay. So this is nothing but we are collecting the elements B in G such that this A and B are related. Here A is fixed. We are collecting B which are related to A. So this set is called equivalence class. Equivalence class of the element A. Equivalent class of the element this one. So we can easily show that this is non-empty because A is related to A. Since it's a reflexive, therefore A is related to A itself. Therefore definitely the CL of A contains A. So CL of A is contained. So that is the CL of any A should be non-empty set because at least one element, namely A, should be in this number. Okay. Now already we know you studied in the UG level. So once we have a relation on a set X, so maybe in general, I can say what is the equivalence relation. Suppose X is a non-empty set. Suppose X is a non-empty set. And suppose we have a relation delta is an equivalence relation. Equivalence relation means what? It satisfies the reflexive, transitive, and then symmetric. So it's an equivalence relation on the set X. Then for any A in or any X in X, take any X in X, we define the equivalent class of X, that is the box X. So this is a collection of all Y in X, that Y is related to X. So this is called the equivalent class of X. Equivalent class of the small x. For each x in X, we have a equivalent class. If we take some other Z in X, Z also equivalent classes. Now, what is the properties of these equivalent classes? The first one is sometimes use this bracket box X, or sometimes use CL of X. Okay, conjugate class of X. Now, this CL of X is always non-empty set because X is related to X. Therefore, this should be, so that is X is a member of CL of X or box X. Because X is related to X, because we assume that delta is an equivalence relation, therefore it's a reflexive, therefore X related to X. This is the first property. Now second, if you take any, either is identical or disjoint. So if you take any two equivalent classes, so let suppose if we take two element X comma Y in X, then we can talk about the equivalent class of X, and then we can talk about the equivalent class of Y. Now the theorem says either both are equal or the intersection contains no elements. That is a equivalent class of X intersection equivalent class of Y should be empty. Either this or this. Any two equivalent classes are either identical or disjoint. This is the second property. Now the third one is, if you take the union of all the equivalent classes, should be whole X. So the X can be written as union of all the equivalent class, where X in X. So that is these equivalent classes form a partition. So partition means what? If you take the union of that set, you will get the whole set, and the collection is called a partition. Now this is true for any set. If you take any set, the set have equivalence relation, then we have equivalent classes for each element. Now here in our case, so this is in the group G, so this is our relation. A is related to B if and only if there exists some C such that A equal to CBC inverse. So this is our relation. This relation satisfies reflexive, transitive, and then symmetry. Then this is an equivalence relation. So once we have equivalence relation, we have an equivalent class for each element. Suppose if we pick one element A in G, the equivalent class of A, or sometimes use the box A. Box A or CL of A is nothing but we are collecting the elements which are related to A. A is fixed. So this set is called the equivalent class of A. And the properties of equivalent classes, we already discussed the now general result. So therefore, if you take any equivalent class of A, is always non-empty set. Suppose if we have two equivalent classes of CL of A, either equal to CL of B, or both are equal. Sorry, intersection is empty. CL of A intersection CL of B is empty, and take the union of all the CL of A, you will get the whole group G. So G is nothing but union of CL of A, where A in G. Okay. Now there is a relation between the CL of A and then this N of A. So what is that? I can say here. So the CL of A is nothing but G by N of A. We can easily show that this N of A is a normal subgroup of G. So therefore, the CL of A, we can even more can say the order of the CL of A should be order of the group G by order of the normalizer of the group, normalizer of the element A. Okay, so order of G by order of N of A is nothing but order of CL of A. So this is a very important equation. The number of elements in the equivalent class of A is nothing but number of elements in G by number of elements in N of A. Using this, we have an important equation. That equation is called class equation. Very important equation. Class equation. Class equation of a group G. Of a group G. So what is the class equation says? If suppose G is a finite group, then G can be, the order of the G can be written as like this. So what is that? Let G be a finite group. Let G be a finite group. Then the order of the group can be written as order of Z of G, that is center of G, plus summation of order of G by order of N of A. But A does not belongs to Z of G. Okay, so actually, or more even, we can say that. So this is nothing but this summation order of CL of A. Okay, so order of CL of A. So A is any element in G. Okay, so suppose suppose if A is in center of G, then what will happen? So there are two. These summations can split into two summation. So namely this. So maybe I can write here. So this is a class equation. Okay, so this this equation. So this equation is called the class equation. Okay. Now how to get this one? Anyway, this is a general form. Order of G is equal to order of CL of A, but the CL of A can be split into two ways. So what will happen? Suppose if A is an element in set of G, then implies what? By the definition of set of G, AB equal to BA for all B in G. Okay, now what I am going to prove, this CL of A contains only one element. If A is an element in set of G, then the CL of A contains only one element, namely A. Because already we know that the CL of A contains A, but if A is a number of set of G, then the CLF contains only one element. Why? Suppose if we take some other element B in CL of A, then what will happen? So that means B is related to A. That means what? B equal to some C times A, C inverse. That means what? You can multiply with C, therefore BC equal to CA. Now, since it's a abelian group, now look at this. No need to go the next step. Since A is an element of Z of G, that means what? This A satisfies the commutative property with every element. In particular, it satisfies the commutative property with this C. Therefore, CA can be written as AC into C inverse. Therefore, C into C inverse identity. Therefore, we get A. Therefore, B equal to A. So, if we start with the arbitrary element in the CL of A, we get that element should be equal to A. Therefore, CL of A contains only one element if A is a member of Z of G. Now, therefore, maybe we call this equation is star. Now, the star can be written as 2 sum. The sum varies over A in Z of G. A does not belong to Z of G. Okay, so therefore, order of the group can be written as summation A runs over Z of G. So another sum is A does not varies Z of G. And this is a order of CL of A. And this is the order of CL of A. But if A is an element of CL, Z of G, then CL of A contains only one element. Therefore, we get the summation is 1 plus 1 plus 1. How many times? Number of elements in order of G. Therefore, this is nothing but order of G. The first summation is nothing but order of G. Now, the second sum should be A does not belong to Z of G. This is very important condition. The summation runs over all the A, but not in Z of G, order of CL of A. But we know that there is a relation between order of CL of A and then N of A. So what is that? This red color. So order of CL of A is nothing but order of G by order of N of A. So this is a classification. So this is equal to order of Z of G, center of the group, plus A does not belongs to Z of G. Order of CL of A can be written as order of G by order of N of A. So this is order of G. So this is a class equation. Very important. Any finite group, the order of the group can be split into this form. Order of Z of G. So clearly, if suppose G is a abelian group, then this become order of Z of G should be equal to order of G. Okay, that should be important. Maybe we will discuss some example if they ask in the Z of G. Oh, okay. Now we discuss some theorems, very important theorems. So there is a relation between this Z of G and then the group. So maybe the first result says, suppose if, since already we know that the Z of G is a normal subgroup, therefore we can talk about the quotient group, G by Z of G, G by the center. Suppose this quotient group is cyclic. Suppose the quotient group is cyclic, if and only if G should be abelian group. G is an abelian. It's very important result. Suppose G by Z of G is cyclic, then G should be abelian. Okay. And then another thing is there are some other thing. Okay. Yesterday I forgot to say that if you take any group of order prime square is always abelian. Group of order prime square, group of order prime square is abelian but need not be cyclic. Why a group of order prime square is abelian but not cyclic? Take the example. Yesterday we discussed about the Cartesian product of the group. Suppose take Z2 cross Z2. Okay, what is the number of elements? So suppose take G equal to the Cartesian product of the group. The number of elements in the group is 4. 4 is nothing but 2 square, so prime square. But this G is not cyclic because the GCD of these 2, 2 is not equal to 1. Therefore, the Cartesian product of two cyclic groups need not be cyclic. Therefore, G is not cyclic. Okay, and already we know that product of two abelian group is always abelian, but the product of two cyclic group need not be cyclic. So when the product of two cyclic group cyclic, the order should be, the GCD should be 1. Okay, so the next one is that is important result. Product of or direct product of abelian groups is always abelian. Direct product of abelian groups, maybe it's a finite abelian group or infinite abelian group, but the direct product of abelian group is always abelian, but direct product of cyclic groups in and be cyclic. Okay, so 1 minute. Okay, so direct product of any, so maybe if you take finite abelian group, again the product is also finite abelian group. If you take infinite abelian group, the direct product also infinite abelian group. But if you take the finite cyclic group, the need not be finite. When the product is finite, the GCD should be 1. GCD of order of the cyclic group should be 1. But in the case of infinite, there is no result. Okay. Okay. Now, what we said this one. Now, what about we discuss about, already we know that the group of order prime is cyclic, every cyclic is abelian. And then here we discuss prime square. Now, what about prime cube? So, suppose a group of order prime cube need not be abelian. Group of order prime cube need not be abelian. Need not be abelian group. So why? What is the example? The standard example is quaternion group. So what is a quaternion group? They usually call Q8. It contains 8 elements. So the elements are -1, +1, -i, +i, j, -j, +j, and then -k, +k. Okay, what is the condition on this one? I square is -1, j square is -1, k square is -1, and what is the product? So maybe usually in the mark in the circle notation. Suppose this is I, and this is j, and this is k. So in the anti-clockwise notation, I into j should be k. Similarly, j into k is I. Again, k into I is j. But if you take the reverse order, j into I should be -k. Again, k into j should be -i. Again, I into k should be -j. So this is a multiplication in this set. Now, what is the order of Q8? There are 8 elements. So 8 is nothing but 2 cube. So prime cube. Now this is not a abelian. Why is not an abelian? Because if you take the element I into j, so I into j is k. But what is j into I? J into I is nothing but -k. Therefore, k not equal to -k. Therefore, this is a non-abelian group. So clearly, this is non-abelian group. But order is 2 cube, that is prime cube, but not abelian. Therefore, group of order prime cube need not be abelian. So this is an example. So this group is called a quaternion group. Quaternion group. Okay. So, but the order of prime square is always abelian. But order of prime cube need not be abelian. Suppose a group of order product of two primes, and when this will be a cyclic group. So the next one is, suppose the group of order is product of two primes, p into q. Okay, we assume that p is a smaller prime than q, and suppose p does not divides 2 minus 1. Is this condition satisfied, then G should be cyclic group. Then G is cyclic. So any group of order PQ where P less than Q and P does not divide Q minus 1, then G should be cyclic group. Suppose any group of order, suppose we have a group of order PQ, P less than Q, PQ are prime numbers, but P divides Q minus 1. In this case, there is a unique non-abelian group of order PQ. Okay, so there exists a unique non-abelian group on this order. Unique abelian group maybe exist, but non-abelian group exists only one. So non-abelian group of order PQ. Provided this condition up. So if P divides Q minus 1, then there is a unique non-abelian group of order PQ. If P divides Q minus 1, it's always cyclic. Every cyclic implies abelian. So these results are very important. Okay. Now, so almost we discussing. Now we have some. So automorphism, already we defined what is isomorphism. So isomorphism is nothing but it's a function from one group to another group. It's a homomorphism and then bijective. Okay. So isomorphism F from a group G1 to G2 is a bijective homomorphism. Bijective as well as homomorphism we say is a isomorphism. So isomorphism F from G1 to G2 is a bijective homomorphism. Suppose if we take isomorphism between domain and codomains of same group, such isomorphism is called automorphism. So that is automorphism. Automorphism is an isomorphism from G to G. Isomorphism from the same group to same group, from G to G. Isomorphism, domain and codomain is the same group. Such an isomorphism called automorphism. Okay, it's very important. Now use the notation AUT out of G. So that is nothing but set of all automorphism. So set of all function F such that F is a function from G to G is isomorphism. We are collect all the isomorphism from G to G, we call it automorphism. This automorphism form a group with respect to composition. Okay, so next the automorphism of the group is a set. This form a group with the composition operation. It's a group, but need not be abelian group. But not in general, composition does not satisfy the commutative property. That is, F composition G not equal to G composition F in general. Okay, so it's not abelian. Why this is true? Maybe you take some example. Okay, why the composition does not satisfy the commutative property? So example, if you take F is a function from R to R defined by f of x equal to some x square, any function, not homomorphism. Okay, any function. Now we take another function G from G to G defined by g of x equal to x plus 1. Now we can talk about f composition G as well as G composition F, because both the function have domain and codomains are same. Now what is f composition G? F circle G at a point x. So by the definition of composition, this is f of G of x. But this is equal to f of, what is G of x? Is nothing but x plus 1. But what is f of something is nothing but you have to square it. So x plus 1 whole square. This is equal to x square plus 2x plus 1. So this is the value of f composition f at a point x. Now what is G composition f at a point x? Is nothing but G of f of x. So it's nothing but G of, what is f of x? X square. What is G of x square? Is nothing but just x square plus 1. Therefore clearly these two are not equal at a point x. Therefore since these two are not equal, therefore f composition G, this function is not equal to this function. Therefore composition need not be satisfied the commutative property. Therefore this automorphism is a collection of functions, bijective function. Bijective, not only bijection, isomorphism function. With respect to composition, this form a group but not an abelian. Okay. Now this is very important group, automorphism of a group. Now in that group we have to give some subgroup. Not only subgroup, it's a normal subgroup. That is some special type of function we are collecting. We are going to collect some special type of automorphism. So that function, so we define the special collection. Suppose if you fix one element A. So let I fix one element A in the group G. Now using this A, I define a new function f suffix A from the group G to group G. So what is the defining? Suppose f A of, if we take any element small g, is going to map AG A inverse. So here A is fixed number. So I'm defining FG, FA of G equal to AG A inverse. We can easily show that this function is isomorphism. Why is an isomorphism? Now we can, first we got to check the homomorphism. So if we take FA of two element G1, G2. So this is nothing but A G1, G2 A inverse by the definition of the function. Now this is equal to A G1. I can take identity element, because multiply with identity element we will get the same element, right? Therefore I can include the identity element here. You can write this one, right? So once again, so this function we have to show that this is 1 1. So that means when we how to prove a function is 1 1, if you take the images are equal, we have to show that the element should be equal. Suppose FA of G1 equal to FA of G2, then what we have to prove? G1 equal to G2. Okay, now what is the definition of this? A G1 A inverse, and this side is A G2 A inverse. Now we can cancel right so in a group the right cancellation, left cancellation is 2. Therefore the right cancellation we can cancel the right element A. Since the group satisfies left cancellation. Therefore, the left cancellation we can cancel A inverse. Therefore, we get G1 equal to G2. So therefore, the function f suffix A is 1 to 1. So we get a function if you fix one element. If you fix one element, we get a function FA, and this FA is homomorphism 1 to 1. Now we have to prove that the function is onto function. If you prove the FA is onto, then automatically it's isomorphism. Since domain and codomains are equal, therefore it's an automorphism. So next we have to claim that the FA is onto function. So onto means what we have to prove? If you give any element in the codomain, we have to find a pre-image. Suppose we take some element. So let B in the codomain. We have to find the element. So find, what is our aim? Find X in domain G such that this F maps to B under the function FA. So we have to find X, such a X exists or not. So just work backward. Suppose exists, then FA of X equal to B implies that what is the definition of FA of X? X A inverse equal to B. We need X. So first we have to cancel this A, therefore X A inverse equal to multiply A inverse both sides, therefore we get A inverse B. Now we can cancel this A inverse, multiply by A left hand side, we get X equal to A inverse BA. Therefore choose X equal to this, we get a pre-image for this element too. Therefore FA of A inverse BA. So by the definition, this is A into this term into A inverse. So what is this term? A inverse BA. Now A inverse A cancel, we get B. Therefore, if you take any element in the codomain, it has a pre-image. Therefore, the function FA is onto function. So since FA is 1, 1 and onto the homomorphism, therefore it's an isomorphism. Since the domain and the codomains of FA is same, therefore it's an automorphism. And this automorphism we call is an inner automorphism. So anyway, this FA is an automorphism. And we call this automorphism as inner automorphism. So therefore, we use the notation INN of G. That is inner automorphism of G is nothing but collection of all the functions of the form FA, where FA is a function from G to G. Automorphism. Automorphism. Okay, and A is any element in G. Okay. This inner automorphism, so this is called the inner automorphism of group G. This is a subgroup, not only subgroup, it's a normal subgroup of automorphism of G. So usually we call this is inner automorphism. Inner automorphism of the group G. Now, what is the relation between this inner automorphism of G and an automorphism of G? So yeah, therefore this inner automorphism INN of G is a subgroup of automorphism of G. And not only is a subgroup, it should be normal subgroup. So this is notation to denote normal subgroup. So this means normal. So this inner automorphism of G is a normal subgroup of automorphism of G. It's a very important result. So the inner automorphisms are look like this one, FA. So therefore this FA of X maps to AX A inverse. This is a function. If you changing A, you will get a new function. Suppose you fix B, then FB of X is nothing but BX B inverse. This is another automorphism. And this automorphism called the inner automorphism. So therefore every inner automorphism is a automorphism, but this is a special type of function. Okay. Suppose I am taking G, suppose a function is of the form G of X equal to some G X G, okay, don't confuse this G and this one. Suppose we have function H of X equal to some L x L inverse, then this H is nothing but F suffix L, this automorphism, this inner automorphism. Okay. Now there is a relation between this inner automorphism. So every group we have inner automorphism. Now the important thing, the quotient of G by Z of G by the center of the group Z of G, this is isomorphic to this inner automorphism of G. Okay, so it's very important result. So sometimes they will ask the number of inner automorphism. So since these are isomorphism, therefore the coordinate of this equal to coordinate of this. Yes, any doubt?
Sir, how did you say it's automorphism, sir? Just
It's
because it's
isomorphism and domain and codon are equal.
isomorphism, we can say it is automorphism, sir.
Yeah, automorphism, because domain and codon are same, that's why we call it automorphism. If the domain and codon are different groups, we call
Sir,
it
we should check
isomorphism.
whether it's not abelian. That and all not needed, sir.
No, why we need abelian here? So we have to
What
say
is
a
the
function is automorphism. First you have to say the homomorphism or not,
Okay,
and then you have
sir.
to check one and on two. It's enough to check that the function is automorphism or not. So group may be anything. Group is either abelian group or non-abelian group.
Okay, sir.
So this is an important result. G by Z of G is isomorphic to. So this we can easily show that this is isomorphism. Why? So we have to define a function from G to Z of G to inner automorphism G. We have to prove that the kernel is Z of G. We have to use the first fundamental theorem of isomorphism. So that is, so we define a function f from G to the inner automorphism of G. So how we define? If we take any f of small element a or g, we are going to define f suffix g. So what is f suffix g? We know that. So f suffix g of any element is nothing but gx g inverse. So this is a function here. So this is a function. Okay, f of g is nothing but f suffix g. Otherwise, more if suppose you are confusing means f is a function, g maps to, so the domain contains everything is a element, but the codomains are function space. So the inner automorphism G is nothing but collection of all functions, but the domains are set of all elements in the group. So we have to assign every element to a function. So this f takes the element g maps to some function here. So that function is nothing but f suffix g. We know about this function f suffix g of x at a point x is nothing but gx g inverse. Now we can easily show that this function is a homomorphism. This f is a homomorphism. So how to check? So that is f of g1 g2. We have to prove this is equal to f of g1 into f of g2. But by the definition, this is f of suffix g1 into g2. Okay. Now we have to prove that this equal to f g1 into f g2. So how to prove this step? So we start with this f suffix g1 g2 at a point x. Okay. Now by the definition, this is g1 g2 x g1 g2 inverse by the definition of the function. Now this is equal to g1 g2 x. Now we know that ab whole inverse is nothing but b inverse a inverse in group theory. So the reverse order. Now therefore we get here g2 inverse g1 inverse. Okay. Now actually we know that this is not a multiplication, this is actually composition. Okay, because within two functions we have an operation is composition. Now we can write this as, look at this one element. So this is one element and this is a usual. Therefore we can write f g1 of the element g2 x g2 inverse. Right. Now again inside this we can write this is f g1 of this g2 x g2 inverse. We can write f suffix g2 of x. Therefore this is a composition. Therefore how we define f g1 composition f suffix g2 of x. Therefore I can cancel the x. Therefore we get this one. Therefore f g1 is nothing but f of g1 into f of g2. That is composition here. Therefore, f of g1 equal f of g1 g2 equal to f of g1 composition f of g2. Because the composition operation in the codomain. So here multiplication is the operation in the domain. Therefore, I am taking here multiplication, but here we take the composition. Therefore, f is a homomorphism. Next, we have to prove that kernel. Again, already we know that every automorphism is of a form. So if we take, we have to prove onto function. So if suppose we fix some function here. So we have to prove onto. So if we take any element of the codomain, at least one element maps to that one. So if you take any arbitrary element, suppose in taking some h is a function, already we know that if you take any automorphism is of the form h suffix some a. So we can choose a here. So because we have we get idea here, therefore pick a in the domain. This a maps to ha. Okay. Therefore clearly this is onto. Now what is the kernel? Kernel is nothing but set of all element which maps to identity element. So what is the kernel of this function? So kernel of f is nothing but collection of all elements g in the domain such that the f suffix g should be identity function. So that means what? So this is equal to set of all g in g. So when we two functions are equal means what? Suppose f is a one function, g is another function. When we say two functions are equal, the functions are equal at each point. That is f of x equal to g of x for every x. Then we say f equal to g. Okay. So therefore this one function, this is the identity function. These two functions are equal means what? These two functions are equal at all the points. So identity of x. But identity x is nothing but just x. Therefore set of all g in g. What is gx? Fg of x is nothing but gx g inverse, and this is equal to identity of x nothing but x, because identity function takes x to x. Now take this g inverse to this side. So what you will get? So set of all g, we are collecting g such that, so this is for every x. For every x in g. So this is nothing but z of g, because we are collecting the elements which are commutative property satisfied with every element. Therefore, the kernel is z of g. By fundamental theorem of first isomorphism theorem, g by kernel is isomorphic to the image. Therefore, g by kernel is z of g now is isomorphic to the image. So image is nothing but now just now we prove this onto function. Therefore, this is isomorphic to inner automorphism. It's very important result. Anyway, all the results are very important. So sometimes they will ask the number of automorphism or number of inner automorphism in a group. Now maybe I will give some formula. So what is the automorphism of integers? Any group we can talk about automorphism, inner automorphism. Therefore, automorphism of z, set of integers. How many automorphism we can define? Therefore, the cardinality is 2. Only 2 automorphism we can define. Okay. Okay. The second is automorphism, the cardinality of automorphism of Zn is pi of n, Euler phi function. The number of automorphism on Zn, that is set of all isomorphism from Zn to Zn, how many function we can define? Pi of n. So pi of n already we know the formula. So first we have to write n is a product of prime powers, and then the pi of n is nothing but n into 1 minus 1 by p1 into 1 minus 1 by p2, etc. 1 minus 1 by pr. So this is the number of automorphism in this one. Suppose they ask, maybe the question may be like a question, let G be a cyclic group of order 10. The number of automorphism. The number of automorphism of G is question they will ask. And we know that any finite cyclic group of order 10, therefore this G should be isomorphic to Z10. Therefore automorphism of G is nothing but is isomorphic to automorphism of Z10. Now we need the cardinality of this one, left hand side is same as the cardinality of this one. So what is the cardinality of automorphism Z10 is nothing but pi of 10. So pi of 10 value is 4. Therefore answer is 4. Suppose instead of they given this finite cyclic group, suppose they give this infinite cyclic group, the number of automorphism is what? And we know that any infinite cyclic group isomorphic to Z, and we know that automorphism Z is 2, therefore automorphism given infinite cyclic group is also 2. So this is an important result. Okay, and you can find the more formulas in my notes. It is available in my website. You can find it there. So any doubt? So anyway, I can stop now. So you can stop the recording.